Assalamu alaikum. My name is Hanan Ahmad and my registration number is 21T25. Today we are going to discuss lab number 8 of DSP. The lab objective is implementation and analysis of moving average filter, implementation and analysis of finite impulse response filter Fourier transform design method. So in the task number 1, define filter. A filter in the context of DSP refers to a system of algorithm that modifies the characteristic of a digital signal. Filters are used to extract, enhance, or suppress specific components of a signal based on their frequency, amplitude, or phase properties. The second question is types of filters. The first type is low pass filter. It allows frequencies below a specified cutoff frequency to pass through. The other type is high pass filter. In this type, it allows frequencies above a specified cutoff frequency to pass through. In the band pass filter, it passes a specified range of frequencies centered around a central frequency. Basically, it is used for isolating specific frequency bands in signals. The last type is band stop filter. It attenuates a specific range of frequencies while allowing frequencies outside the notch to pass through. So the third question is time domain parameters for a filter. The first one is step response. In this, a good step response indicates that the filter settles quickly and smoothly to its final steady state value without significant overshoot or oscillations. While the second is overshoot, a low or negligible overshoot is desirable as it indicates that the filter output closely matches the desired response without significant deviation or transient effects. The third one is linear phase. Linear phase is considered beneficial as it ensures that all frequency components of the input signal experience the same phase shift, preserving the signal's waveform and avoiding phase distortion. The question number 4 is what are the frequency domain parameter for a filter? The first one is roll off. A good roll off refers to the rate at which a filter's frequency response decreases from the passband to the stop band. The second one is ripple in passband. A good filter has a minimal or negligible ripple in the passband, meaning that the magnitude response remains relatively flat and consistent across the desired frequency range. The third one is poor stop band attenuation. In this, good stop band attenuation refers to the filter's ability to effectively suppress frequencies outside the desired passband, ensuring that unwanted signals, noise, and interference are adequately attenuated or eliminated. In question number 5, we have to discuss the role of low pass filter for filter designing. The main purpose for a low pass filter in filter designing includes selecting desired frequencies while blocking higher frequencies, and the second one is preventing aliasing in digital signal processing. The task number 2 is plot the signal in time and frequency domain along with its magnitude response. So the given signal is x range from 1 to 40, that is equal to 0. So the input code will be, first of all we define the function, that is x is equal to 0s, and then use subplot command, and then use stem command to plot the discrete graph, and then title these graph where x label is as sample index and the y label is amplitude. After this we use FFT command, and then we find magnitude response. Again we use subplot command, then stem, and also labeling this. We repeat this process 2 to 3 times, and when we simulate this code we obtained this output. As we can see, the first one is signal in time domain, and the second one is magnitude response, and the third one is signal in frequency domain. The second part of this task is as same above, but the x range from 41 to 120. So we repeat the same task as above. just change the value of the signal and simulate this code. And the third part is also same, while the range are different. So in this part we change the value of x and then plot this code. When we simulate this code, we obtain this output. As we can see, first is signal in time domain, and the second is magnitude response, and the third one is signal in frequency domain. And the fourth part of this task is range from 121 to 161. We change the value of x in the above code and then simulate this code. We obtain these output. So the last one is in this part, it is also same as the above. We define the function x is equal to zeros, range from 1 to 161. First of all, we add noise to the x. Then define the moving average filter. After this, we apply moving average filter, then plot the filtered signal, and then compute the Fourier transform by using FFT command, and then find the magnitude response. And when we simulate this code, we obtain this output. First one is filtered signal in time domain, the second one is magnitude response, and the third one is filtered signal in frequency domain. In the next part, we have given 3 tap. Number of tap is equal to 3. Symmetrically around moving average filter on signal x of noise and observe time at frequency domain parameters. We use the same code as above, just change the number of taps that is given is equal to 3, and then simulate this code. We obtain this output. First one is as same, filtered signal, then magnitude response, and then filtered signal in frequency domain. The other part is also same. In this part we have given number of tap is equal to 11. Just use the above code and change the number of tap and then simulate this code. We obtain this output. In the third part, we have given number of tap is equal to 25. Change the code according to the number of tap and then simulate this code. We also obtain these output. So the task number 3 is, the first part is repeat example 7.2 with 7 tap, 17 tap, 51 tap and 101 tap, and observe the frequency domain parameters. Let's see the code for this. First of all, we have number of tap is equal to 7, then cutoff frequency that is 800 and the sampling rate is 8000. So first of all, calculate the normalized cutoff frequency, then calculate filter coefficients, then display the filter coefficients. After this, we determine the transfer function, then convert the transfer function into symbolic form for equation manipulator, and then display the transfer function in symbolic form. Then determine the difference equation using the filter coefficient, and then compute and plot the magnitude frequency response. Then use plot command and then labeling these graph, and then if we want to mark specific frequencies, then we use this plot. The frequency points that we want to mark is 0 into 1 by 4, 1 by 2, 3 into 5 by 4, 5. And when we simulate this code, we obtain this output. As we can see, in second part, the number of taps coefficients are 51. Just we use the same code as above and change the number of n is equal to 51, and then when we simulate this code, we obtain this output as we have 51 taps obtained, and the magnitude frequency response is as above, and the mark command that is used to plot these points, as we can see. So in this part, we have to plot example for 101 coefficients. Just use same code and simulate. Then we find these magnitude frequency response. In the part B, apply the filters made in part A to the signal Observe the changes for signal x in time and frequency domain. So the source code is sampling frequency is 8000 and x1, x2 and x3 are given. So the total signal will be obtained by adding these signals. Then plot the original signal. For this we use subplot command, title and labeling these graph, and then plot the original signal in frequency domain. We also use plot command in this. Then design and apply FIR filters with varying number of coefficients. That we have 17, 51 and 101. And then simulate this code. We obtain this output as we can see. So in the task 4, we have to repeat example 7.3 with 7 tap, 17 tap, 51 tap and 101 tap, and observe the frequency domain parameters. So the number of tap for first part will be 17 and the sampling frequency is 8000 and cutoff frequency is 2000. Cutoff frequency in hertz upper is 2400. First of all, normalize the frequencies. Then calculate the bandpass filter coefficients and display the filter coefficients, and then convert the transfer function to symbolic form of equation manipulation. After this, display the transfer function in symbolic form. Then use plotting commands. We use plot and then label the graph and grid on. When we simulate this code, we obtain this output for 17 tap FIR. In the part B, first of all, sampling frequency is 8000 and the signal as same. But here is the number of taps has been changed. So when we simulate this code, we obtain this output.